And today I want to present my work on semi-supervised monotonic regression for calibrating social media classifiers. So I will start with the main motivation behind this work. As we all know that oversampling is a frequent problem, and we frequently use a technique that we use it, especially when we are dealing with low label prevalence ML problems that will fit to many of these integrity problems, abuse detections. These are usually rare problems, and we want to train a classifier on them. And to make sure that the classifier has good quality, we usually will having some oversampling. Also, when we're dealing with underrepresented languages, we want to train the models on globally, on many, many languages. We always have this kind of issue in oversampling. And of course, this naturally leads to sampling bias. And there are many sources of the oversampling. The most common one is using ML assistant sampling. Basically, when we use an ML model and we want to rely that model, if the ML model, the score of the model is positive, we want to oversample that to basically increase the chance of having more positive classes. But there are other ways to do that. For example, domain-based sampling, when we have these integrity issues and we believe there are some domains that are most associated with these issues, we want to oversample some samples from those domains with the proposed with links. Active learning methods to use some kind of uncertainty, find which samples will leave more uncertainty and asking labelers to label them. And also it's very common to oversample underrepresentative languages. So as I mentioned, there are some advantages in oversampling. Obviously, we want to classify to be more, observe more classes of positives, especially when we are dealing with very, very rare classes, and also better understand all languages. But on the other hand, the prediction is not representative because we trained on oversampled population, and it could have higher scores for certain tasks. So it may not, the population, the output population may be not representative, and it has for some certain tasks, it generates higher scores, for some tasks, smaller scores depending to the oversampling algorithm. And it will create some language bias. Some languages have maybe higher scores, generate higher scores, some language lower scores. And the one that is mostly we care about is that the calibration model cannot fix this bias. So there are some techniques to use weights to debias these oversampling, but I will show that those techniques are not enough to debias that. There are other also motivations behind this work. For example, we usually have a lack of enough high quality samples, especially when we dealing with real world problems. Sometimes you have budgeting problems, human annotation is expensive, or maybe it's the quality of the labels are different. On some languages, maybe we have high quality labels, and some languages lower quality. Sometimes the labels are subjective. It's very hard to label them. Also, when we want to launch a new product, we have also problems. We need to ask labelers to label them. It takes a long time. It may be a little bit noisy at the beginning. And there are some existing approaches such as few-shot learning, but they have also other product limitations. So the solution that we want to propose today is basically using semi-supervised approach. And we want to use a population level prevalence data as a leverage it to deal with this bias. There are many ways to use this population level data. For example, we can use the view prevalence. Basically, that means that the prevalence, the proportion of positive samples that viewed by the users. For example, if we have for some issue in social media, 2% of users exposed to that problem, that's a population level data. Or with top post prevalence, the posts that are very top in social media, or comments, the proportion of comments that the user exposed and have issues in social media. And basically the main idea is using a semi-supervised approach and leveraging population level data to augment our training data and work against this sampling bias. And the method that we want to use is called learning from label proportions, or LLP. And the main idea is that we divide our data up, same as any semi-supervised approach to labeled and unlabeled data. The labeled data is just a traditional of machine learning part, but on unlabeled data, we split data to a set of soft constraints. And each constraint could be, for example, language. For example, we divide it to different languages. I will explain more about constraints later. And then for each constraint, we know what is the positive label prevalence. So that's all, we call it the per knowledge of the population. So for example, we know, our per knowledge is that for English posts have roughly 5% positive rate. So this is a per knowledge for English. Or random sample of comments have roughly 3% of positive rates. We want to leverage this population level data and train a classifier. And to do that, we propose using a deep neural network or generating any neural network. And there are two approaches. The first approach that I want to propose today is basically based on dividing each batch to a set of mini batches. And then for each mini batch, we have samples for one constraint. For example, for each batch, one has English, another one has Spanish, and others. And the main advantage is that this is easier to implement. But on the other hand, in order to train this model, we need to have a relatively large batch size because we want to divide batch size to smaller batches. So it's not suitable if we have an expensive, huge model. And the second approach is that we divide, each batch has basically only samples from one constraint. If you're interested, this paper has an implementation of that. You can follow on that. The main advantage is that we can use it for any large neural networks, but the problem is that it's hard to implement because you need to rearrange batches, especially if you have a multi-GPU settings. You need to rearrange batches between these GPUs to make sure each batch has its samples from same batch. But for the purpose of today, we use the first approach. And this graph shows the main idea behind this learning from label proportions approach. Basically, as I mentioned, we divided our batch, split it to mini batches, and one of these mini batches have labeled samples. It's basically supervised approach using binary cross entropy or similar multinomial or similar methods to compute the computation loss. And some of these, they don't have any label. And those are the one that we are interested. For example, we have some samples from comments. And for that, we compute the posterior probability of that mini batch. And what our target is making the prior probability and posterior probability closer to each other. And the posterior probability, we call it CEP, or classifier estimated prevalence. It's basically the average of model scores, weighted average over the class samples, label samples. And we want to compare it to our pure knowledge. And we can use any distance function. What we found is that using the KL divergence works better as a distance function, but we can use mean square or other distance functions. And then we will add all of these things together to compute the batch loss. And we will have some parameters for each batch to somehow regularize how much the model needs to pay attention to labeled samples, how much to unlabeled samples. By the way, if you have any questions, just feel free to interrupt me. And now I want to talk about the model calibration. So the main application for today's talk is more than using this method for model calibration, but there are other applications. So you can use LLP for even the model classification. So why do we need the calibration? This is very important because sometimes the model need to be interpreted. For example, when the model returns a score of 0.2, it's basically just a number between 0 to 1. It's meaningless. But if we calibrate it, then it has a meaning. That means that 20% of time, the prediction is correct. So basically, if the sample population, all of the samples that we point to a score, we would expect 20% of them are to be positive if we have a good calibration model. Another advantage of calibrating model is having a better classifier estimate prevalence, or CP. This is very important because in social media, we want to track issues. And we cannot always rely just on the label data. So label data has its own noises, it has some delays, and it's sometimes we want to know what is the prevalence of issues in different surfaces, different contents, different based on photo, video, but we have this limitation on label data. But having a high quality classifier estimate prevalence helps us to understand the prevalence of issues. Finally, we often use these models in a downstream. So there are other models trained on the output of another model as a feature. And if we have a calibrated model, the downstream models also work better. So the advantage of using semi-supervised for calibration, model calibration, is that supervised methods often miscalibrated because of these natural bias in sampling bias in the training data. And the semi-supervised learning, we can fix that bias. And we can use the constraint as a random sample of population that we want to calibrate on it, and use the prior label-based prevalence as a prior knowledge. There are some existing calibration methods, but they're not suitable for semi-supervised settings, because in our setting, we want a neural network approach, but all of them are based on neural network. As a result, we propose and introduce our own approach. It's a small neural network to do the calibration. So yeah, I wanted to explain about our approach. Basically, first, let me define the monotonic function. I'm sure all of you are familiar with that. The monotonic function is always increasing. And the reason that we are interested in monotonic function is that because the calibration is always monotonic. So if the probability, if the off scores of two contents, one of another is higher, after the calibration also we want to keep that. And these are some samples of monotonic functions such as sigmoid, tangent hyperbolic, or any linear function with positive slope is a monotonic function. But we are interested on the especially monotonic functions that starts from 0 to 1. Because in calibration, we want to calibrate the score 0 to 0 and 1 to 1. And this slide shows some characteristics of monotonic functions. These are very basic characteristics. It's very easy to prove that sum of multiple monotonic functions always positive monotonic, and also the composition of two monotonic functions is also a monotonic function. And by putting these two characteristics together, we can easily find that this function here is a monotonic function. It's basically, we have a linear function here with positive slope, it's monotonic, and then we have a sigmoid, and the composition is monotonic, and then we have sum over it, and it's monotonic. Basically, we can generate a monotonic random functions here. And for the last piece, to make sure that the function starts from 0 to 1, we just need to apply simple normalization. We need to subtract f of 0 and divide it to f of 1 minus f of 0. And this is also monotonic because we're just subtracting it constant and dividing it to it constant. So this slide just summarizes everything that I mentioned. To create a simple neural network that always generates a monotonic function, start from 0, 1. It's differentiable function. That means that we can use gradient descent or other optimization algorithm to train our models. And we can use it in semi-supervised setting. So we call this as monotonic regression or monotonic calibration. And when we use it in semi-supervised learning, we just call it as semi-calibration. This slide summarizes differences between these monotonic calibration that I explained and some baselines. The isotonic regression is very popular, very simple regression or calibration. It's very popular. It's very simple. It's based supervised approach. The main problem with it is that it generates some isotonic beams of samples, basically map beams of samples to a single number. And you can see that on the plot on the right side. So this plot, the x-axis is uncalibrated score, and the y-axis is calibrated score. As you can see, the isotonic, this green one here, you can see those beams. Beta is in state-of-the-art calibration method. It's based on label data, so supervised approach, and it also generates a continuous function. It's not like isotonic, it's continuous. The monotonic approach is the one that I explained in the previous slide. It's based on label data. Again, it's continuous. It's very similar to beta. And the semi-supervised learning is, again, same as monotonic, but trained on semi-supervised settings. It can use unlabeled data to correct the sampling. In order to evaluate our models, our calibration models, we need a good metric. So in supervised approach, they usually use calibration coefficient or calibration curve to measure the quality of the model. But here, the requirement is slightly different. So we modified the definition of calibration coefficient, and we want to measure basically the distance between prior knowledge and the posterior knowledge. So that is our main target. So we want to make prior and posterior to be close to each other. And again, the prior is the average of positive class weighted on class weights. It's the label-based prevalence. And the posterior is the classifiers weight prevalence, average of calibrated scores weighted on class weights. And we define calibration coefficient as prior divided posterior of label-based prevalence divided by classifiers weight prevalence. And this, we would expect this score would be closer to 1. So basically, if it's 1, if we have a very good, perfect calibration. So we use some real-world data to evaluate our models, and we apply this on the different baiting problems we had in social media, especially in Facebook. And one of them is called engagement bait. It's basically a tactic that users use to interact with Facebook posts and ask people to like or share or comments to artificially boost their engagement and get greater reach. And most users, they don't like to see these posts, and they don't want to interact with them. And another one is clickbait. That's also popular. Basically, these are some headlines intentionally omit some crucial information or exaggerate the details of a story to make it seem like a bigger than it is really. Basically, these are some baiting posts with some URL, and somehow they want to trick user to click on the URL. And when you click on it, you'll probably go to a site with lots of ads or some misinformation. And we have two types of this. We have withholding. Basically, they withhold information from the readers, and they exaggerate the article to create some misleading expectation for the readers. And our classifier trained on different modalities. We use post, and these are some of the modalities, and we have more modalities. We use the post text, link text, especially link title. It's very important, especially for clickbait, because clickbait involves with the link. Text extracted from photo, from OCR, video transcript, if there is a video, and we have a bunch of photo and video pre-trained features to train our models. But the main focus today is not the model itself, it's more about the calibration. In order to train our calibration model in semi-supervised settings, we divided our model data to 4 sets. So the training and validation is similar to any supervised approach. We use the training for model training and the validation for model validation. But we also use the validation data for calibrating our model as a training data. And then we have a calibration data that is data without any label, and we want to use it for semi-supervised calibration. And then we have a testing without any label, just random sample of population for testing the calibration. So this slide shows the result of using different calibration methods on engagement rate, clickbait exaggerate, and clickbait withholding. And again, we would expect that the calibration coefficient closer to 1 is always better. As you can see that all of the supervised approach, they have very similar calibration coefficient for engagement bait and clickbait. You can see they under calibrating, meaning that the kernel probability is slightly, actually for clickbait even more, they're smaller than the posterior probability. But semi-supervised learning somehow fixed that. For engagement bait, it's almost very perfect. It's very close to 1. For clickbait, it's closer to 1 for exaggerate. And for withholding, with the isotonic beta and monotonic calibration, somehow over-calibrating because the score is more than 1. But by using the semi-supervised learning, it's closer to 1. It's 10% higher than posterior. Also, we looked at the result by different languages. We use engagement bait for this analysis with 27 languages. Again, we use the calibration coefficient and compute the average of coefficient, and closer to 1 is better. The first row in this table shows the result, the average coefficient. As you can see, isotonic beta and monotonic, they're struggling, they have lower average, but the semi-supervised learning worked very well. In average, the average score is 1. But of course, it has some variation per language. We'll look at the language, and we call some languages that they have a calibration score between 85 to 1.15. We call them well calibrated. Basically, they are within 15% of error. And as we can find that for a supervised approach, there are only 5-6 languages well calibrated, but by using the semi-supervised learning, we can increase it to more, 10 languages now well calibrated. In order also to evaluate this on a publicly available data, we use also IMDB review data. It's basically sentiment-based data. It's very balanced data. It has 50% positive, 50% negatives. But in order to simulate this, we change the proportion of positives and negatives. We use the same approach as before. We split data to 4 sets. We reserved 8,000 for training, and we trained a simple logistic regression model here with precision recall of 87%. And we have a validation and of 8,000 samples. For calibration and testing, we use up to 16 or up to 15,000, depending to the simulation. So in order to simulate the sampling bias, we under samples negatives or undersample positives. So for example, in first row, we reduce number of negatives to make it 15% of the population. And in order to fix that, we increase the weight for negatives to cancel that bias and use that to train our models. And same for other rows. And as you can see, is that weight alone is not enough for supervised approach. And all of this supervised approach are under calibrating the population. However, the semi-supervised approach could outperform all of them, and the calibration coefficient is very closer to 1. This slide shows the calibration map it compares beta calibration and semi-supervised learning. For example, if you look at the blue one here for prevalence of positive prevalence of 5% in the left side, and if you compare it with right side, you can see that under calibrating issue that I mentioned. Basically, if you just put this together, you can see that the left side is always lower than the right side. That's what we call it under calibration. In order to use this calibration, because the social media data is dynamic, we need to have a recurrent calibration. And these are the steps that we do to calibrate our models. Basically, in first step, we use the label data in some training windows, let's say, for example, last 30 days or 15 days, whatever. And then we use samples, random sample of our population on same window. And then we train our models every day. And we evaluate the model and we measure calibration coefficient and other metrics to make sure that the model, the calibration has high quality. And if it has a high quality, we can push it to the prod. So this slide shows how we can select constraints. And we can use this constraint for model training or for model calibration, for both of them. There are many ways to do that. For example, you can use some correlation analysis. I will explain more in the next slide. And using the label-based prevalence, that's the one that I already explained. You can use precision of model. Let's say, for example, if you know that the precision of model is 70%, that means if we sample from sample post with predicted at positive, 70% of them are positive. We can break it down to languages and use prevalence of each language. We can break it down to photos, videos, or body type. And also, it's also okay to have overlap between these constraints, so we shouldn't worry about that. And it's usually better to choose constraint that has higher prevalence, especially for model training. So these are some examples that I mentioned before. For example, 5% of comments are positive. The second one is basically based on the correlation analysis. For example, we found that 10% of all samples with more than 300 comments are positive. So we can use this piece of information and use that. The third one is the precision I explained. And the last one is 4% of English samples are positive. So in future, we want to expand it to other applications. As we explained, this approach is feasible and good catch when we are dealing with models trained on oversample data or on multilingual data. Also, there are some use cases that we need multiple measurements and we want to calibrate on multiple measurements. For example, if we want to calibrate models based on watch time or based on comment on different surfaces. And when we have a lack of data, but we have good domain knowledge, it could be some alternative to few-shot learning. And when we have good correlation analysis, that we can generate good constraints. Yeah, in future, we want to expand this work to smaller batch size, as I mentioned at the beginning, for bigger models. We want also to remove label reliance. So basically, we can get rid of the label data at all and just use the unlabeled data in unsupervised learning. And we want to use some programmatic way to generate good constraints or using some information retrieval methods to generate constraints. Thank you so much. Any question?
Thank you, Hassan. Let's thank the speaker first. We have a question in the room.
Hi, Hassan. Thanks for that. Can you give an intuition as to what the unlabeled samples are doing here? I'm struggling to work out how they help calibration. So some sort of intuition here would be great.
The intuition of using unlabeled samples?
Yeah, and I guess beyond that, you mentioned you want to go only to unlabeled samples, which just seems like straightforwardly impossible, but maybe obviously I'm confused about how you could calibrate with no labels.
Yeah, so first of all, this is not just for model calibration. So we can use this approach on even on model training. But let's say you have some labels from before and you have some expectation, but for some reason you want to stop that because very budgeting, we want to stop it, but we don't some good estimate that 5% of problem for post have positive. So you can use that prior knowledge to continue train the model also, even though you don't have a new labels. Of course, there is a pros and cons, that the distribution could change over time, but it's possible. And there are also other ways to do that based on different source of truths. For example, we can use demographic attributes. For example, one example is for politicals. When you have a polls and you know, for example, this county have 60% voting for Democrat, and you can use that as a population data and sample data from that county, and you could expect that 60% of them positive. So basically, you can use some domain knowledge or other source of truth to use that.
Does this answer the question? Yeah. Thank you, Hassan. So one question from my side: what is the catch of this approach? So is there like a computational cost, something that would prevent someone to use it?
Yeah. So the main problem here, the main catch, is the quality of this classifier estimated prevalence. And with this model, we can create a model that has a very high quality classifier estimate prevalence that match to the label data. And as a result, it will have high impact on downstream that are using this classifier for demotion or training different models. That would be the main catch here for this approach.
Sounds good. Any other question? Yeah.
If you go to your previous slide where you were showing this as a regularization, we know that when you introduce regularization, it has a cost on the performance, so it lowers precision or recall. Or is there any such effect that will be observed with this particular approach?
Yeah, so that's actually a good question. So for model calibration, this approach doesn't change the precision recall. It just changed the distribution of the scores. That's for the model calibration. But for model training, what we observed, because we also use this approach for model training, what we observed that the precision recall doesn't change again, not much. However, it's because it's learning from the data in a different way from unlabeled sample. When we use this model, it has impact on downstream. So these are the things that basically learn from the data, some hidden accept of data. And we cannot measure it based on label data, but it has impact on the downstream.
Thank you.
Last question is this available open source? Probably not, but so given some of the questions in the audience, so maybe people have difficulty understanding how would this be applied in practice, so how are the labels? So I'm not sure if the team is considering that. I'm pretty close to the work, so I assume not, but just wanted to make sure.
Yeah, I think we can create and publish it as an open source. Yeah.
All right. Thank you again, Hassan. Thank you for the talk. Let's thank the speaker.